Hello, everybody, and welcome to the first episode of our new webinar, Read and Talk About Gemology. My name is Justin K. Prim, and I'm going to be one of your hosts for this series. And just want to say hi and thank you to everybody for being with us and joining us on the first evening of our first episode. So, without much delay, I will invite in Vincent, our other host, and he will explain a little bit of the concept behind this new webinar. Hi, Vincent.
Hello, Christine. Yeah, everybody, hello. So yeah, this is tonight the first of a series of a new version of our webinar, because instead of meeting once a week and speak about field gemology, we are going to meet now once a month, and the idea is about to promote a little bit some good article and some good books on getting some time and motivate people to read more about gemology and talk a little bit about it, because we found out that there are great articles and there are also some great books about gemology that we read. And sometimes there is something missing, and the missing thing is that the author. Sometimes I found out that it's actually very interesting to hear a little bit what the author has to say about how he went to writing such a piece of article, such a book. And there is a lot of untold stories that is actually very interesting and can be very motivating for young people like me and you, willing to study a little bit more and to learn more about gemstone and gemology.
Yeah.
So that's the idea behind it.
So yeah, I think this is going to be cool. We're going to get the opportunity to talk to a lot more people than than was our scope for field gemology talks, because of course now we can really speak to anyone who's ever written anything, in the world of gemology and gems. So we should have a good time, and we have some interesting guests in mind for the next few months and maybe the
Mm.
next few years. Who knows how long we'll
Well,
maintain this one.
yeah, we'll see. But for sure, regarding going to the field all the time, you remember what I say, I repeat and repeat. The first thing to do is to read as much as you can about the place you are going, about the stone you are going to see, in order to get ready. Because when people ask me all the time which is the kind of the best instrument to bring to the field, my usual answer is a good brain full of knowledge.
Yeah.
So this is something very easy to carry. It's just very light. Knowledge is light, and you just have to spend maybe 20 or 30 hours before an expedition to read and to dig, in order to get most of what you need to do that. But without reading, it can be a real disaster. So
Yeah.
yeah, there are many people that have written some very good piece, and I would be very happy to invite them to speak and to have a discussion with them about their work.
Yeah. So who are we going to be talking to tonight? First episode, first conversation. Who's our guest?
Well, tonight our guest will be Emily Dubinsky. She's a gemologist, and she was my colleague when we were working at GIA. And I decided to ask Emily to be our first guest because at the beginning, when we started the field gemology department at GIA, we were collecting sample, and then slowly and slowly we had quite a lot of sample, and we are starting to work on this sample. That was not really our thing, really, at the field gemology department. My task was more to collect the sample. But very soon, GA decided that data collection had to go on. And they sent Emily to Bangkok in order to help doing that and
Mm.
to set up the thing correctly. And thanks to him, Emily work for 1 year, we were able to really advance on that. We were able to advance a lot on sample fabrication to make sure that the sample were fabricated correctly and that data were collected correctly. So I had the pleasure to work with Emily on the sapphire from Kataragama when these stones were discovered in 2012, and also several other deposits like Didi and sapphire from northeastern Madagascar. And she really pushed us quite hard, and it was great because we improved a lot. And I have a lot of admiration for the work that she did, because she was dealing with some very complicated things, and she was able to turn that into some articles that are, kind of very technical. Yeah. But if you take the time to read and to digest all that, it's actually very useful. Yeah. And I recommend strongly to anybody who wants to study gemology and kind of modern gemology and lab gemology to seriously consider to read these articles.
Okay. Well, shall we invite her in and she can tell us a little bit about herself and the article, of course, and what we're going to talk about tonight. So Emily, whenever you're ready, you can unmute, start your video, and join the party.
All right. Thank you guys for having me. I am delighted to be your first guest in this series.
Welcome.
No, it was a pleasure. It's all the time a pleasure to see you, and it was really a pleasure to work with you for the time you spent in Bangkok. It was very educative for us. It was tough, but educative.
Educating for me as well, and exciting. I had never been to Thailand before. Well, one short trip for GIA, but that long trip was my first large exposure. So it was a fantastic opportunity, and I think we had a lot of fun working on all those fantastic samples that you collected.
Wow. Yeah. So you almost did kind of a blind move then, just uprooted and moved to the other side of the world.
Yeah, the assignment was initially supposed to be 3 months, and I got there and started working, and Ken Scarrett, who was running the Bangkok lab at the time, was happy with what I was doing, and Vincent and I were having a good time working together, and so Ken kept extending my stay. So I did. I showed up with a couple suitcases and then stayed a year.
Wow. Jeez. So,
well, we miss you when you left. Huh? We miss you a lot when you left.
I missed you guys too.
So Emily, well, I guess maybe just to get started, because this is the background of this talk is about an article that you wrote. Maybe could we just get a really brief idea of what the article is about, and then we'll get into the backstory of how it all unfolded and how it all came about.
Sure. So the article is a quantitative study of all the different trace elements that cause color in ruby and sapphire. So corundum is the mineral, and then the gem varieties are ruby, which is the red version, and sapphire, which is every other color. And so what we were trying to do in our work is to look at each of the different causes of color in isolation and quantify what's called their absorption cross-section, which is essentially their strength of absorption. So how efficient they are at producing color, so how strongly they absorb light. And so we worked through that issue, and it was really 10 years of work because we worked on the problem, went back, refined the work, and ultimately came up with the G&G paper that was just published last month.
Cool. Okay. And so before we get too deep in the article, let's get a little bit of info about you. First of all, where are you coming from right now? Where are you at? It looks like you have a beautiful scenery coming up behind you in the window.
Yeah, and it's not a Zoom background. That is real. So I'm coming at you live from my family's hometown in Steamboat Springs, Colorado.
Cool.
I live full-time in New York, but I sneak out to the mountains when I can to get a little fresh air and space.
Okay. And so,
wish I could do that.
So can you tell us a bit about kind of your background? How did you get into gemology? Did you go through the higher education system, or did you circumvent it like I did, or maybe you did a third way?
Yeah, well, I guess the third way would be I had sort of meandered my way in and out of academia and professional life along my career trajectory. So my background is, as you can tell, I'm in Colorado. I love the outdoors. And so when I went off to college, I very quickly decided I was going to become a geology major, and I was very passionate about that. So I majored in geology undergrad, had a great time doing that, and was so interested in it and loved the academic setting of college that I thought, I want to become a professor, go into academia, and to do that, I need to go to graduate school in geology. And so my senior year in college, I decided I was going to go straight on to graduate school. So I shopped around PhD programs and selected one at Stanford, where there was a professor working on a very niche issue in experimental geochemistry that I had had exposure to the summer before my senior year. So I went off to graduate school straight out of undergrad, got to a big research university, spent a few years there, and looked around and said, I don't think I really want to go into academia. I want to take this in a different direction. And what I was studying was essentially the short range order of silicate melts. So it's sort of like studying the atomic structure of melted minerals. So it was like tangentially related to gemology. And I've always loved gemstones. That's always been another interest of mine, like out hiking in the mountains, rock hounding. And so I decided to leave graduate school and pursue a career in the gem and jewelry industry. And in order to do that, I realized I needed credentials in the gem and jewelry industry. So fairly immediately after finishing my graduate work, I enrolled in GIA's Graduate Gemologist Diploma program by distance. And at the time, I was still living in Northern California, and I did most of the GG program by distance and got to the end, the Gem Ident portion of the course, and realized, oh shoot, like that's very intensive to get all this equipment and look at all these gemstones. And I'm at a point in my life where I have a lot of flexibility. I'll move to the Carlsbad campus and finish my GG there, and then I'm going to explore next steps in the gem and jewelry industry. And at the time I was thinking, I think I'd like to open my own custom design firm. But so I got to GIA's Carlsbad campus, finished my GG, and just by chance there was a job fair that fall. And there was a position open being advertised for technical editor of gems and gemology. And the position had been open for over a year because they were looking for someone who had an advanced degree in a related science, chemistry, physics, geology, material science, and a graduate gemologist diploma. And there aren't that many people floating around at any given time that have both of those. Mm-hmm. And so I applied, and at the time Alice Keller was editor-in-chief of G&G, and it didn't take that long for me to get hired on. So I was hired on as technical editor of Gems and Gemology. Spent about 9 months doing that before I was poached into the laboratory division in GIA. And at the time, the laboratory said, hey, we really need more colored stone gemologists, but we actually have enough in the Carlsbad location. We really would like some more in New York. Would you be open to moving there? And I said, yeah, why not? I'm always happy to explore. I've never lived in New York, or actually I've never lived in a big city. Like, let's do this. Sounds fun. So I was transferred to New York. And about a year and a half later, that is when the opportunity arose to travel the Bangkok lab and work on the country of origin database for ruby and sapphire. So I did that for a year, came back to New York, and was sitting in the seat and looking around. And I love doing research, but I also had this entrepreneurial drive that I really did want to start that company that I'd always thought about starting. And so eventually, as I was, getting older, I realized this is my chance. If I'm going to do it, I got to, launch off and do it. And in order for me to feel comfortable going into the business side of gems and jewelry, I really would prefer to do an MBA first. So I ended up doing my MBA in New York City, left GIA, did the MBA full time, and actually then did a meandering side track onto Wall Street for a couple of years, because that's the pipeline out of a lot of MBA programs, is go work on Wall Street. So that's what I did. And as I was doing that, I still had connections on 47th Street, which is the Diamond District in New York. And I was having a lot of friends and family ask me to make jewelry for them. And I was friends with bench jewelers and stone dealers. And so I was doing design on the side. I wasn't allowed to have a side business at the firm where I worked. So I just did it for fun. And one of my teammates at Goldman said, Emily, like, this is crazy. You're so good at this, and you're so passionate about it, and you're differentiated. You could do this as a career. You need to leave Goldman and do that. And I was hard-headed for about a year and a half. And finally, it was this moment where I was like, she's right. And I do have the opportunity, and I've situated myself with all the skills and connections that I need to start the jewelry business that I had originally been dreaming of. So that is my circuitous route through the gem and jewelry industry. And yeah.
Wow,
And
that's.
this is what you are doing now.
And this is what I'm doing now. Yes. So I run my own custom design firm based in New York. And I'm also, sneak peek, the chief product officer of a new jewelry startup that is set to launch in mid-October.
Cool.
And that one is a company where we are looking at applying sustainability principles to engagement rings. So stay tuned to that and follow me on social media, and you'll see a lot of updates about that in the coming week or two.
Very cool. So I guess the move out to New York was somewhat life-changing because you never left.
Yeah, it was absolutely changed my world. Yeah, I miss California, but New York has been, a place rich with opportunities to explore. So it's been fun, and adjusting to the urban lifestyle was a big adjustment, but I'm pretty much used to it now. I live near Central Park, so I can see green space, which the outdoors woman in me really, really needed.
Yeah. Okay, so let's get into the paper a little bit. I mean, you kind of gave us a little bit of the foundations of where this started, right? Because I think, if I'm not mistaken, you started in some level, you started writing, or at least working on this project while you were still with GIA.
Yeah, so actually, I can dive into the background of all this work, which is very interesting, and it was a very peculiar and unique situation that arose at GIA. So what had happened at GIA, and this was around 2009, 2010, is that GIA realized that it would be very helpful for them to give their gemologists even more foundational training in the technical aspects of gemstones. So, and it was Ken Scarrett who really led this, founded it, have a good grounding in chemistry, physics, that sort of thing. And Ken Scarrett elicited the help of John Emmett, who is a retired physicist who used to run Lawrence Livermore National Laboratory's R&D program. And John had become involved since his retirement as a physicist, and so he had a close relationship with Ken, and would consult for GIA. And Ken elicited John's help in training a small group of gemologists. And so the course that they put together, we called Corundum 101. And what it was that John, every month for several years, had a group of 6 gemologists come to his home outside of Portland, Oregon. And for a weekend, one weekend every month, he would lecture to us on the physics and chemistry of corundum, trying to treatment affects it, that sort of thing. And as part of that course, that's where all work. So we would go back to the GIA labs and fabricate samples that were singly doped with the different colorants of corundum, and work out the spectra and chemistry of those samples. So that is where the work really started. And it was, a lot of uphill battles, technical challenges, trying to figure out that work and get it technically correct. So that's why the work has taken so long and been refined over so many years.
Okay. And so
I still remember about and that was true when John was saying that at the beginning. I was thinking, wow, I was a little bit shocked, because John was looking at all the publication about gemology and the work that gemologists were doing, and he said that basically he didn't know anybody who was a good scientist and a good gemologist. Say, oh, there are some people that are very good gemologists, okay. Some people are very good scientists, but he didn't know anybody who was both, according to his definition, a good gemologist and a good scientist. And he decided to try to groom some people who will be, good gemologists and good scientists at the same time. And that was, I think, a very brilliant idea, because, this training, this Corundum 101, this course that you had the chance to go through, was pretty amazing.
Yeah, I mean, it was very unusual. I'm not sure that GIA has done anything quite the same, but it took a tremendous amount of resources because once a month, two of us from the New York lab would fly to John's house. Two women would fly all the way from Bangkok for a weekend. But it essentially, with the travel on either end, it would be the better part of a week that they'd be tied up. And we had one gemologist come up from Carlsbad and one who was local in the Portland area. And it was, I mean, the resources and support that GIA threw at that were really tremendous. And I was very grateful for the opportunity because it was really important that that work be done and then subsequently shared with other gemologists on staff. And as I was going through the course and towards the end of it, I repackaged some of the lectures that John had given us and shared them with staff in the New York, Carlsbad, and Bangkok laboratories. So it was a great way I had much appreciation for the fact that GIA pushed us to not only learn the information, but to disseminate it amongst the staff.
Yeah, no, it was wonderful. GIA did a tremendous job with that, and we all benefited. People working in the lab in Bangkok, I was, wow, that was great. I was even more motivated, to collect a good sample because I knew that there were some people that, in the lab who will produce very good data about that. And we were doing something that was going to be very useful to gemology. So that was super motivating. Yeah.
And so I'm guessing just from knowing that, John was one of the co-authors for this article, is this Corundum 101 class where all this kind of started, like when you met John, or how did that all unfold?
Yeah, well, John had been working on Corundum before this class started, but the actual work on quantifying the absorption strength, the absorption cross sections of the different chromophores really started in that class, working on that in a directed manner. And so we'd work out a chromophore at a time. John would provide us with samples to work on, and most of the samples that we worked on were laboratory grown samples that were very pure, just had that one trace element of interest that we wanted to study in them. And we would go off and do the spectroscopy and the analytical chemistry on the samples and put together, oh yeah, there are the samples. So what you're looking at there are each of those different samples represents a different chromophore of Corundum. And there are all laboratory grown except for the upper right and lower left. The upper right corner is representative of trivalent iron in Corundum that in high concentrations makes that nice yellow color. And in the lower left, that is a blue sapphire from Yogo Gulch in Montana in the US, a location that's known for having very chemically homogeneous samples. So that was something that we needed when we were studying because we didn't want color zoning, which color zoning is the equivalent of, by and large, chemical zoning in the samples. And so the first time that John and I presented the work to the public was after Corundum 101 finished. That's right, the timing of that. The first time that we publicly shared any of the data as we were working on it, and we'd worked through all the different colorants at that point, was at the World of Gems conference in 2012 in Chicago. And so we put together a presentation, and we also wrote an accompanying paper that is a condensed version of the G&G article that's now available online. And
it was in the guide, published in the guide.
Yeah, exactly. Yes, and that was exciting that was our first time publishing it, and that was 2013. And so then the history of the work was I left GIA in 2014, and was kind of off doing my my MBA world. And so my business school program was 2 years long, and at the very beginning of the second year, John called me up and he said, Emily, I have a question for you. Would you be interested in continuing to work on these chromophore issues and writing up a chapter for Dick Hughes' updated edition of his book, Ruby and Sapphire. He's asked me if I will write a chapter and contribute a chapter on our work, the causes of color in Corundum. And I had discovered by that point in business school that business school actually doesn't require necessarily all that much time working on your homework. So I said, oh, I think I have the bandwidth to do that. And that sounds really fun. And I would feel really good about helping with that. And it would be my way to continue to give back and share what I've learned from that Corundum 101 opportunity. So it was the winter of 2015, 2016. John and I painstakingly labored and put together a very long chapter for Dick Hughes' book, and with the help of Ken Scarrett. And that came out and was available to the public in 2017. And some of the audience probably has the book and is familiar with it. It is weighing down my coffee table now. The shelf is literally bowing because it must weigh 20 pounds. Yeah. Yes, it is giant. I mean, it's basically my favorite book in the world, but some people in the gemological community started saying, well, this is so great that you published this research, but it's, I don't have the book. I can't get a hold of the book. It would be great if the information was available online. And so in 2019, after John and I were getting this feedback, we reconvened and we said, we would feel even better about making the data available if it was available online, and not just the written up paper, right? But also the actual data, because that's data that can be used, it's useful. And so in 2019, we worked on putting together the G&G paper. And in doing that, it was actually an interesting endeavor because we realized that what we needed to also include was additional information, supplemental information. First, it kind of explaining the physics of what a cross-section is, right? The conceptual basis for that. But we also realized that what was really important was to do a good, thorough write-up of uniaxial crystal optics, because when you look at the paper and you look at the spectra, you have to recognize that you have spectra that were collected with the crystal in two different orientations, because corundum absorbs light differently in different directions. And to read that paper, it is very useful to also refresh or learn about crystal optics of uniaxial crystals. So that actually was an interesting, side track in putting together the whole paper, because it's one of those things that I've had exposure to that kind of stuff in my mineralogy classes. When I was an undergraduate, when I was in graduate school, I took material science classes. But being forced to then write it up in a way that would be familiar and recognizable and understandable to a gemological community actually was one of the bigger challenges of the paper, especially because I personally don't think in 3D really well. And so trying to, do the crystal diagram and explain it all in words was really challenging.
Yeah.
I was super happy when I saw the article published in G&G. And I saw also that what I really like is the three versions are different. The one in the guide is great because it explains a little bit where spectroscopy started with Anderson and things like that. So you have a kind of crash course about spectroscopy from the hand spectroscope to the photospectrometer. And then in Ruby and Sapphire, you have something more extensive. And now in this third one, you explain well about the cross-section and everything, which is, in my opinion, is very useful because it seems that, you have continued working on it. And there was a lot of work between article number 1, article number 2, and article number 2, and article number 3. So it was great. I really like it. Even if it's not a definitive thing, because you speak about the main colors for corundum, but actually there might be some more that are contributing a little bit less, like unstable color centers and things like that are a little bit not well explained still now. So
I mean, anytime you do research, that's what's fun, right? Is that you still walk away when you publish a paper with more questions that you have because you've noticed this or you've noticed that. for sure. So there
You
are
might have to do a paper number 4, actually.
paper number 4. Well, for sure. Like, well, so I mean, one plan for a paper, right, is in the long chapter that we published in DQ's book, we not only talk about the chromophores in isolation, but then the thing about chromophores is when you have more than one in a sample, their absorption spectra just sum. So it's very easy once you understand how each one behaves in isolation, you can just add them together, right? Layer them on top of each other, or overlay them, I really should say. And so that is a very interesting paper that I think I need to get in gear and, get beyond just the outline of it, but actually talking about the different combinations and how you think about that.
Yes, correct. And this is what is very useful when we work in a lab, because most of the natural stones we have are not just one, chromophore. There are several things that are at the same time. So when we look at a stone and when we get a spectra, most of the time it is a combination of several things that you explain in the article. And so we can, when we get that and we understand that, we can play a bit with the spectra. And then we can double check, for example, the information coming from the chemistry. And we can see if, oh, the chemistry says that, with that chemistry, I should have this color, but the color is a bit different. So maybe there is something else. So, being able to, dismantle the spectra, it's very, very useful. When you want to know if the chemistry makes sense, if all the data you have is making sense. So it's great.
Right. And using UV-Vis spectroscopy to understand the color is a lot more robust than a typical analytical method in the lab is laser ablation, inductively coupled plasma, mass spectroscopy, right? LAICPMS. And that technique, you're just ablating, a small hole, the width of a human hair. So you're just looking at the chemistry of like a little spot. But like what causes the color in an entire gemstone is the whole volume, right? And when you do a spectrum, you're looking at, a long slice through a sample. So using LAICPMS and thinking that you understand the chemistry would be a bit like taking, 1 teaspoon out of a swimming pool, analyzing it and saying, oh, I know, the composition of all the water.
If the gemstone was perfectly even, that would be useful. But sadly, sometimes, and most of the time, they are not even. That's why it's good to have, when you do LAICPMS, it's actually good to do LAICPMS in different areas where the color might be different, and then recombine all that.
Right. Yeah. And that's fine for research samples, but if you're eventually going to apply these sort of techniques to client stones when you're working in a gemological laboratory and issuing reports, clients don't like it if you make a million little holes on their stone. One or two or three on the girdle is fine, but you can't go blasting the whole thing. So, but with UV-Vis, that's non-destructive, so you can absolutely, investigate the stone as much as you want that way.
Yep. Mm-hmm.
And so, okay, so this third paper is sort of a continuation of the first and the second, right? But it wasn't a continuous work. I mean, there were some gaps in between. So how did that experience work? Or how did you guys work with that experience in terms of, was there new information, or had you guys had some sort of new illumination in the time between the writing of those papers?
What we had done is improved our chemical analyses as one part of it, collected better spectra, but a big piece of it was we, in our earlier papers, our earlier work, we were using for our chemical analyses of the samples, LAICPMS data that had been collected at the GIA laboratories. And eventually we decided to use another technique called SIMS, and we use Caltech's facilities for that because GIA doesn't have that type of instrument. But so that gave us improved accuracy and sensitivity for the chemical concentration of the different chromophores in our samples, which is when you're doing this work and working out, the cross-section, and you need to know the exact concentration. And if, whatever error there is in that, then that's a source of error in your absorption cross-section calculation. So trying to minimize all sources of error was really important in getting it as technically correct as we could.
Yeah. So tell us a little bit about the the chromophores themselves. And I know you have in the article, you have all these different colored dots kind of explaining what you guys were looking for and what you guys found. So tell us a little bit about that, and I'll pop up one of these pictures with the chromophore concentrations.
Perfect. Yeah, so we looked at all the major causes of color in corundum, and this illustration that you have up on the screen now was sort of our this was our summary illustration of what we learned about the absorption strength of all the different colorants, right? So on the left, you have trivalent iron, and what you're looking at, the numbers below, are the concentration of that trace element that would be required to cause the depth of color illustrated by the color circle. So you can see it takes nearly 3,000 ppma of trivalent iron to make that nice yellow color, which was an interesting discovery or thing to illustrate, I should say, because, the conventional wisdom in gemology is that iron makes corundum yellow. Well, that's part true, because if you have just trivalent iron and you have 100 ppma of it, it makes no color, right? And you can make those color circles with the data because you can model any size and concentration and show the color. So the next chromophore in terms of absorption strength is vanadium. And vanadium is actually what's responsible for color change sapphire. So when you look at vanadium absorption spectra using different light sources or illumination, you'll see that it actually produces a different color. So all these circles are using D65 illumination, which is more or less the paper presented color circles under A illumination, so incandescent light, which is much richer in longer wavelengths or warmer colors. And vanadium, when you look at what colors produced under that light source, it's like a purpley color to see and actually illustrate for vanadium, because color change sapphire, what was actually responsible for the color change, wasn't well known from knowing that chromium makes ruby red, and it's also a moderately strong absorber. And then you start getting into chromophores that are stronger absorbers. So iron titanium pairs, to make that blue color that you see on the screen, it only takes 4 ppma. So it's pretty strong. And then you move into the weird exotic trapped hole color centers, which are very interesting to study because they're very strong absorbers. So what a trapped hole is an oxygen atom, right? That there's a hole there because there should be an electron there, but there's not. So it's an electron hole. And that is, if that occurs in isolation in corundum, the crystal wouldn't be electrostatically charged relative to the lattice. And that can be fine as long as they're near others that are kind of in the opposite direction so that they balance each other out. So you have trapped holes that can associate near iron and near chromium, and they're very strong absorbers, as you can see from the color circles, where it's less than a ppma in I think these circles are 1 centimeter path length, so it's a small stone. Less than one part per million atomic. It's like having, if you had a salt shaker, it would be a few grains and it would color the whole thing bright orange or bright yellow orange. So they're, very interesting chromophores in corundum.
No trap hole associated with vanadium?
No.
Vanadium-3? No.
So, over the course of putting together this research and figuring these things out, was there some unexpected, like information that came out of it, or any surprises when you guys were researching these things?
Yeah. So one of the things that came out of it that I mentioned was that, we could wave our hands and say, iron doesn't, it's not just iron that makes corundum yellow, right? Because you have yellow corundum that has under 100 ppma of iron or 200 ppma of iron, like not 3000 ppma of iron. So that was a really important thing to illustrate, right? Is that the conventional wisdom, if there's iron, that's what's making it yellow. Like sometimes that yellow is actually trapped whole. Another interesting thing that we are still scratching our heads about is, when you look at the chromium color circles, you'll notice they're magenta, right? And this caught our eye very early on in the research is, until you get to concentrations that are like beyond what you really would find in a natural stone, and the color circles kind of turn this brick red, the color is really magenta. And so again, it's like the conventional wisdom is, well, chromium, makes ruby red. And so that's, likely mostly true. But what we're looking at now is, we said, hey, you know what would add, if you've got, because you're thinking about color and mixing like you're painting, if you have like a really bluish red, like that magenta color, what's going to make it ruby red is something that's more orangey. And it's like, well, what could be there, in very small concentrations that nobody would have noticed before or even known how to quantify? And the answer is trapped holes. Mm-hmm. So we're thinking through that. Another thing that, was interesting to notice as we were working through the color circle calculations is when you model green in corundum, and you can see these color circles are published in Dick Hughes' book, and they need to be included in the forthcoming paper. But when you try and map out green in corundum, and so the way that I would map out, I would basically make these two-dimensional plots, and I would combine different concentrations of two colorants. And so when I was doing that for green, I'd add yellow, I'd add blue in different concentrations, and you can't make emerald green. The spectra just, when you sun them in the way that they absorb light, you don't get emerald green, and that's what you actually see in nature. You've probably never seen a, natural corundum with a really intense saturated emerald green color. And the same is true when you model. You just can't get that color. You can get kind of mossy green. You can get the weird like chartreuse green. You can get teal kind of spruce, anything you could want but emerald green.
Okay, I guess that's kind of interesting, just to, we see this happening in nature, and then you kind of have gone the other way around and scientifically, explored it and said, oh yeah, okay, this makes sense. This is why.
Yeah. There's no hidden deposits, I would venture to say, of intense green corundum out there that we should be searching for.
Yeah.
Probably no surprise on that side.
No.
So
sadly, no, but
we have a
well,
question
luckily, when you see, if you want to have a nice saturated green done by chromium, well, you switch to a beryl, and then you have an emerald. It's, chromium is in a different type of crystal. The absorption will create a green color that will be maybe more pleasant. So you just have to change the chromium from one corundum crystal to a beryl crystal, and then you have suddenly a lot of very nice green.
Right, which actually now I should, make this point very explicitly, is all these absorption cross-sections that we measured, those only apply to these trace elements in corundum. So you couldn't take these spectra and say, oh, chromium, I've got a chromium spectrum now, and I can, this represents beryl too, or, anything like that.
But maybe
this is all corundum specific.
It will be interesting for somebody to look at that, for example, and moved from corundum to maybe chrysoberyl, and then to beryl, in order to see all this, you
want to ramp up. Yeah, but if you want to like sort of ramp up and not have it be overly challenging to begin with, I would suggest starting with an optically isotropic gem material, right? So you only have to measure one spectrum instead of, because that's a big technical challenge in the work, is that we had to fabricate samples that were crystallographically oriented, and they had to be, as you well know from the research samples that we worked on, they had to be perfect. So we made wafers where the C-axis of the crystal, so the optic axis of the crystal, was perpendicular to the wafer face, right? So we had these parallel window wafers, and the C-axis had to be absolutely perpendicular, like within a degree. It couldn't be off more than that. And it's actually very challenging. We were using special orientation devices that John Emmett, with the help of Tim Thomas, had designed for GIA. And it's technically challenging to get the samples oriented correctly and get them on a dop that you then put in a polishing machine, and keeping that surface absolutely perfectly flat. And then getting a mirror polish on it.
Remember that.
A lot of the research time was fabricating samples.
And so, just as you were,
it took us nearly half a year to get through the challenge of, collecting the sample was some kind of easy, and then we had, okay, let's build the database, and then let's do the fabrication correct. That was kind of several months of work, and then data collection was starting. But data collection, there was no common sense to start data collection if the sample were not fabricated correctly.
Right.
So we had to deal with, and that was the great fascinating thing with all these things that started with the field gemology program, is, okay, we had the samples that were collected correctly, and then, okay, we need a database, we need a photography that had to be correct, and then the fabrication of the sample, and then the spectroscopy, and then. So it was a whole chain of challenge that we had to go through. That was incredible.
Well, the issue too, and we absolutely ran into this quite a bit for the country of origin database where we were working on natural samples, is that for inclusion photography, you want samples with lots of inclusions. But when you're doing spectroscopy, you want clean samples, you want no inclusions, because the issue is when the spectrophotometer beam hits those inclusions, the light scatters, and the instrument essentially reads that as absorption. So you're getting sort of these false absorption readings if you have samples with lots of inclusions. And so it was very challenging to make sure that we had the right suite of samples so that we could do good microscopy work and also do good spectroscopy work.
I remember the challenge that John was putting on us to get, Vincent, you have to get samples that doesn't have particles. I say, but how come, 99% of the sample of the stone I see in the field, they have particles. You say, well, okay, get the 1%. Oh, they have to be big and clean it off. And, oh my God.
Please don't get, it was basically, I was asking.
No fracture, no twinning. Oh my God, I had to go through sample in order to find the 1 or 2 or 3 sample with the right color, where we were able to do the spectroscopy, because this sample had to get through the thing in order to be qualified by Emily. And Emily was saying, Vincent, not good enough, not good enough. Because there is one thing that you put in the article that is very correct with absorption spectroscopy, is the zero. You have to get the zero. So you have to get somewhere, a perfect sample in order to get, when you read the spectra, you read basically the absorption of everything. Bad alignments, internal reflection, minute particle, inclusion, everything. So if you want to have a reference sample, you have to try to minimize all these things that you don't want. And
right. And so when you look at the spectra that are published in our paper, you'll see where it's absorbing. That's where you see the sharp lines and the broad bands. But then in the areas where it's not absorbing light, the spectrum goes very closer to zero. And so the issue and there's no inclusions, fractures, whatever to scatter light. So what you see if you have a sample with inclusions or fractures or whatever is you'll see the spectrum of the chromophore, but essentially the baseline will be shifted up and slanted a little bit toward the shorter wavelength side because scatters more toward shorter wavelengths. And it was interesting. I actually played some games and that's the fun thing about color circle calculations is in order to illustrate to the laboratory, like, this is why it's important to get spectra right, I actually did the modeling. So if you had an imperfect baseline, right, and your spectrum was shifted up, what would the color calculation be? Which was a very visual way to show this is error. And so what I found was, I modeled just like a scatter, and then I added that to the spectra of the chromophores, and you start getting colors that are off and funky and wrong. And so if you're trying to use spectroscopy to understand color in a precise way, you have to have good spectroscopy. And another big issue when we were working on our samples, so there's not only scatter, but you also have reflections off of the surfaces of the samples. And that was an issue that we had to work through when we were working out our cross sections, and a technique that we improved upon as we went, because what we started doing is, so when you have a sample in a spectrometer beam and the beam comes through, you get reflections off the surfaces, and you get internal reflections, right? And they go back and forth and back and forth. And there's a fancy equation, for that. And so when we first started working on our samples, the way that we dealt with reflections was, when you collect a spectrum, first what you do is collect a baseline spectrum, and that's just an open beam spectrum. And then you collect the spectrum sample. So what we did to correct for that loss from reflections was, when we were collecting the baseline spectrum, we had a very pure corundum disk. So like virtually nothing in it, just like, looked like, glass or whatever, but like pure corundum is just colorless. So we had a wafer that just fit over the beam, and we would put it in the beam. And so there would be scatter off of that. So essentially then you correct for that in the baseline, and then you go and collect your spectrum, and you've accounted for the reflections. But then we decided to get sophisticated and fancy, and we actually took that fancy mathematical equation, the Sellmeier equation, and figured out a closed form solution to it. And then you can actually use that, and that tells you accounts for reflections, along the spectrum at different wavelengths. And so we could then basically like subtract that from our spectra and correct in that way. And that's the route that we eventually went. And that was, an interesting sort of challenge to tackle and a rabbit hole to go down and to do. I can't do that kind of like sophisticated, programming type thing on my own. And so we had Scott Hempel, who is a researcher at GIA, help us with that and write up this spreadsheet that we could then use, and in concert with our data to get them as good as we could.
You see, Justine, what was interesting with all that, somewhere I could think at a point, it's all this complication. It will take us so much time to collect data. But there is one thing that is very interesting about all this thing is how to collect data. What is a reference stone? A reference stone, a reference spectrum, it's something you can use to compare with another one. The difficulty when you collect data on two stones is if you don't collect data the same way, there is no reason why you can compare. So you have to set some rules in order to have, a way to compare the data from stone number one with the data from stone number two. And that makes sense scientifically. And this is where it's very important to have a reference stone and to set some rules about, and to know exactly what you are doing. Okay, we are collecting the data this way in order to be able to compare the data from stone number one with stone number two. And in order to be able to understand if maybe this stone, there is something funny in the spectrum, maybe it was heated, or, maybe find something that will enable us to lead to maybe an origin, some information about origin or some information about treatment. And this is where it's super important to go to all these details in order to make sure that we can compare stone number one and stone number two. And stone number one, you keep it as a reference, then it becomes a reference stone. You have to do the job perfectly one time, and then you can use that data as a reference with other stones. And that's the critical thing, that it was a challenge, it was a huge challenge. And this is where Emily spent 1 year hammering us about that. because basically she was not satisfied with 95% okay. No, 99% something that was acceptable, but less than 1%, more than 1% was not okay.
Mhm. True. And you know, another issue when you're using this kind of technique is not only do you have to work on different stones in a similar manner, but if you're working on a single stone, you have to be very precise.
Mm.
A good example of this is, okay, first of all, like when we were collecting a spectrum composition at the point that we're going through, so you want to make sure that the chemistry matches that point exactly. So you need to do your chemistry analysis on that exact spot. It has to be that exact spot in the stone. And when you're, so you can use this kind of technique to study, say, heat treated stones, right? So if you want to understand how the color has changed before, like after heat treatment, you've got to, you know, shoot the beam through the stone, heat treat the stone. It's less informative if you go back and look through a different part of the stone. You need to go right back through that same beam line basically that you shot through the first time to really understand in a quantitative way the changes that happened. And so the way that we worked on our samples is, again, another innovation and modification that we had to make to our instruments is that Tim Thomas, who at the time was doing instrumentation for GIA, developed these sample holders that could fit into spectrometers. And so eventually that was like a piece that held like a little sample plate. And the sample plate was a rectangular aluminum, you know, it's like about the size of a credit card, and it had a little well in the center. And in that well was a hole that had been drilled. And so what you would do is you'd put your sample over that hole. And then you've got this little like well that's like a little mini swimming pool for wax that you would melt around the sample to hold the sample in place. And so then you could, once the wax had hardened, you could pop the sample in and out. And there was only, because each sample had a, you know, funny outline, there was only one way that it could go into that wax that would hold it in place. So you knew you were always in that little hole that was drilled through. Well, that's where you'd aim your spectrometer beam. And you always knew that you were going through the exact same spot in the sample. Yeah. Which was like, again, like another one of those things that when you're doing this kind of research, you run into all these sorts of issues that you've got to, you know, figure out a way to manage, and it can take a lot of work to.
I remember when you started to tell us that we had to go to that, but then, you know, at the end on all the articles we did at GA after your input, you know, starting from 2012, you can see this every time, you know, the stone in the stone holder with the wax. And every time, you know, infrared spectroscopy, UVV spectroscopy, and also chemistry was collected exactly the same place. And for chemistry, for trace element chemistry, basically we were collecting the trace element chemistry 4 spots on every side of the sample. So there was 4 spots on one side of the wafer and 4 spots on the other side of the wafer. So like that, we had a more chance to get something that was statistically correct. And we were trying to compare, is the chemistry we get from LEIC PMS compared to UV visible? Does it make sense? Or maybe there is something that, you know, is the sample even? The sample is not even? What is the coloration? Thing like that. So all this process was put together when, you know, during these 8 months, 8-9 months when you were in Bangkok wow. At the end, when I saw the Kataragama article on the other one, I was happy. You know, I was happy. I said, well, it was hell. It was a lot of work, but at least, you know, there is something solid here.
Yeah, I still remember you coming back with like those Kataragama sapphires, and they were very like big and gemmy, and it was very exciting that we were going to have some, you know, stuff for spectroscopy.
It was the stones that were coming from there, where you had some significant stones, some very nice sapphire. And it was, you know, it was a gem rush. There is all the time something exciting about gem rush. And I wanted to make sure that we'll be able to make a good article and set up the way for other article to be done. We had to set up basically a protocol, and we were working together. That was our task. Vincent, you collect a sample, you work with Emily, you work with Kai, you work with Pooh, and we all team up together in order to make a first article correct, and then you duplicate with the other one. So we had to set up the rule, and it was exciting teamwork. Yeah. Great teamwork. That was great.
Sure.
So Emily, let me pose a few questions from the audience for you. I've got one from Mubashir Mansour. So you were just a minute ago talking about, you know, making those models, and sometimes they were telling you if you had made a mistake or something. So he was asking, can you please elaborate on the models, and you know, are you referring to a specific computational method, or how did you do it?
Okay, so the way that I produced all of the color circles in the paper, and anytime I wanted to essentially make a model, some sort of theoretical model of color in corundum, the way that I would do that is the starting point is the absorption cross-section spectra of the samples, right? And so that is the absorption strength of each chromophore, which is independent of its concentration or the sample size. So that's the starting point. And then what you do is you say, okay, I want to model a particular size and concentration, and it's just a linear relationship. So it's just a simple multiplication factor. And so you basically scale the cross-section spectrum that way in a spectral processing program. And I was using grams. It is Thermo Fisher grams, and it's a spectral processing program. And so what you do is you basically create your theoretical absorption spectrum in absorbance units. And then you convert it to transmission, because you do color circle calculations with transmission spectra. And that is a kind of a translation that the computer program will do for you. You literally like click and drop down menu and say, convert absorbance to transmission units. So then that's your starting point. And again, the software also has color coordinate calculations. And so built into this processing program are the color calculation equations. And so again, you press a button and tell it, you tell the program, I want you to calculate the color of this spectrum, and you specify, the most important thing that you specify is the light source. And so I would choose either A or D65 and go from there. And what happens is you literally press a button in the program and it spits out color coordinates to you, and you can choose which color coordinate system you want to use. And I use CIE, L star, A star, B star, because it's a very uniform color space. And so you get these three coordinates, and okay, that's the color. And so you have to, translate that into a visual color. So then I would go to a program like Photoshop and draft, and very simple, like draft a circle. And then, in something like Photoshop, rather than just like when you fill in something with paint, you can actually fill in and specify the color coordinates. And the program asks you, what are the L star, A star, B star? And you just type them in and it pops up. And I'll still never forget. I mean, the first time I ever did this,
we lost her?
Right? And I'd never done it before, and none of us had done ruby wafer, and it was very thin, so it was pale pink, and got the color coordinates from that, and it was just like amazing. And it was one of those, you iron out all the kinks, where I had to learn that I had to use transmission spectra instead of absorption spectra, because if you do color circle calculations using the absorption spectra, it's basically like more or less, but not exactly upside down. So I was just using absorption spectra and getting black color circles. I don't understand what's happening, and I eventually figured it out. But that's how I made all the color circles, and that's how I play these games with like, what would happen if the baseline was shifted up? What would happen if there were 100 extra ppma of this colorant or that colorant? So it's a really fun way to do some sort of predictive modeling. And it's very helpful too for if you're thinking about how heat treatment or any other treatment might affect a stone. And this is really where, so John had done color circles long before I had, and this is I believe one of the first times he did it was he was helping GIA at the time, and this is before I was at GIA, understand how much, I believe it was titanium diffusion, would color stones blue. And so he was using color circles to say, okay, if there's this much more titanium, maybe he was doing decoloring. Maybe it was titanium. It was blue sapphires. So let's say theoretically this is the example though, right? What you could do is say, okay, if a stone is titanium diffused, and let's estimate that there would be X ppma more, 100 ppma more, 50 ppma more of titanium that would be available for iron titanium pairs. So therefore, let's say that there are 50 more iron titanium pairs, after titanium diffusion, like how much bluer would the stone get? And so you can do those kinds of calculations. Same that you can do with beryllium diffusion, which beryllium diffusion introduces trapped holes into corundum, which then create the trapped hole associated with iron or chromium. So you can figure out, how much trapped hole would it take, say, let's say you had a pink sapphire, and you wanted to figure out how much would it take to make it into a nice Padparaksha sapphire. And, in most cases, the answer is just, a few ppma, depends on the size of the stone. But all those sort of games and models you can play with this technique.
So cool. And so really when you do your calculation and you get your color coordinates, you plot them into Photoshop, and then if you're holding that stone that you took the sample of and your Photoshop isn't matching, then somewhere something went wrong.
Something went wrong. You need to go dig a little deeper.
That's it's kind of a cool check though. So then you can really know, like, we're doing this correct. We're not.
Number one, you need to be sure that your screen is color calibrated correctly.
That too.
Number one.
Yet another rabbit hole that we went down.
Oh my God, I remember that also.
Yeah, right? Like all these things that you have to, I still have nightmares of that. There was that thing that at GIA, they had the thing that you stuck on your monitor to calibrate the monitor. And but all of that, it made a difference when you're trying to get things as correct as you can. Yeah, you've got to think about all things. And
I was not too much doing the color circle, but I know that Kai, when she was doing that, and that was not really my part of the thing, but I tried to color calibrate my computer. At least I did that 3 or 4 times. I have to say I should do it more, but I did that 2 or 3 times, and then I was not using too much color circle. I really like the story behind and the whole thing, but field gemology, I was trying to get the sample, I was not on the,
Right.
I did that 3 or 4 times. It was a bit a painful thing.
Okay, so here's another question, and you were just speaking about trapped holes, and Mubashir had another question specifically about that. So he was asking, isn't there any influence of the cause of the hole on spectrum? He had always thought the hole contributor can shift D-shell orbitals, but the generalization you've made he said, it's quite interesting and revolutionary for him. Does that make sense?
Interesting. That sounds like a question from a physicist and material scientist that
he's a material
starting to dig into electron shell orbitals is going beyond the scope of my area of expertise.
That question was beyond this area of my expertise, so that's okay. I don't even know what he's talking about. So, okay, so maybe that will be a question for another day.
I wish if I had John Emmett on. It's too bad I can't phone a friend right now and ask John Emmett, because he would have a terrific answer. I'm 100% sure.
Okay, I got a couple more as well. These are from Martin Viala. He was asking, copper and manganese, for example, are known chromophore in several mineral species, but not naturally associated with corundum. Would they act as a chromophore if you were to dope synthetic sapphires with such elements? What do you think?
That's a good question. I'd need to look up the ionic radii of those 2 elements. The fact that you don't see them much, right, suggests that they probably don't because of their size, fit so well into the corundum lattice. Which isn't to say that you couldn't stuff them or pack them in there if you grew a sample that was doped with them. So that's a good question. But the fact that you don't see them suggests that it's not so easy to get them into the lattice to make color.
Every time there was some suspicion of that, we check with, I never saw any corundum, natural corundum synthetic with any copper and manganese. No.
Yeah. So it turned, like, the corundum lattice is pretty rigid, right? So there's not a lot, the trace elements need to fit pretty efficiently in there. It's difficult to either expand or contract and squish other stuff in. But the question with manganese and copper?
Yeah.
Yeah.
And his other question was, what is your favorite chromophore in corundum?
Oh, that's a good one. That's a good one. I mean, so on a sort of, I would say, like a theoretical philosophical plane, what I think is so cool about the trapped hole is like this concept of like what causes color is something that isn't there, right? Usually we attribute something to something, and here it's like something there's something not there. So that to me is kind of fascinating. I got really intrigued though with the I go back and forth. It's the mixtures of chromophores that I find so interesting. So, when I first made up my 2D array of purple, I just, was in love with purple. Then I found green really interesting because it sort of skipped a region of green color space. It's hard not to love Podparasha color. But yeah, I go back and forth. I think like right now I've sort of fixated on the green. That's just for like purely visual reasons at this point. And that's what I love about corundum, right? Is like I have trouble like just having one fixed favorite color, and I'm very lucky that corundum comes in virtually every color, and so I can there's always a version of corundum that is my current favorite color. And a lot of the jewelry I design actually is corundum because I get a lot of it from a supplier who sources it from Montana, so it's responsibly sourced. And then I love it because it's essentially from my hometown backyard in the Rocky Mountains of the U.S. And it's beautiful stuff. And a lot of it is the blues are blues that are have a component of green, which I actually prefer that to the straight blue color.
Yeah. So when you were doing your research and doing all these calculations, how many of these color circles did you end up making? Like there's not a ton of them in the article, but I imagine you had like hundreds of them or something.
Hundreds, yeah. Getting it all right and exploring, and not so much in the book or in the paper or the book, but to figure out for the 2D arrays, like what space I wanted to show and what concentrations were the right concentrations to illustrate in a way that kind of transitions smoothly across the region of color space. That took a lot of work to figure out. And it's fairly labor intensive to do those color circles, right? Because you've got to do the spectral multiplication on the spectrum, convert it to transmission, get the color translated in a program, and then make that color and then put it in an actual illustration. So I wish I was a computer programmer because that should be something that's easily automated, but again, beyond the scope of what I can do because I do not know how to code.
Yeah. Okay, here's another question that I think this is another question that I'm not really this is out of my realm, but I will attempt to transmit this question to you. So this is from Goran Newald. He's asking, I think that an evaluation calculation of the Brillouin zone of the reciprocal lattice would allow some insight into the theory of the placement of ions for manganese, copper into the corundum structure. Does that make sense?
Oh, interesting. Okay. Yeah. Hi, Goran. So I'm like reaching, oh, I see somebody's making a comment too. I'm reaching back in my mind to what I learned about atomic structure in a crystallography class a million years ago. So that certainly ties into what I learned there. And I would have to think through that a little bit more before I could comment much further on it. But you reach out, Goran, with that question again. I want to read it carefully and think about it.
So, okay, you guys have done this, these 3 articles, 10 years of work, and the one that just came out last month. So the data's out now, more than you were able to put into Richard's book. The actual data's in the new article. So how can active gemologists use this information now in their, whether it's in research or day-to-day work?
So all the spectral files are available to download online. So if you have access to any sort of spectral processing program that can do color circle calculations, you can take our absorption cross-sections. And if you look in the paper, you'll see the mathematical relationship between cross-section and size and concentration. So you can use the data to actually do the modeling yourself. Which is really helpful. You can also use the spectra if you have the cross-section spectra, if you have spectra of natural samples and you're trying to understand the different color centers that are in it, because you can basically like subtract out the different chromophores that are in the natural sample using the cross sections, and that gives you insight into how much of each one is there, because based on how much you subtract out, that's how much would be there, if that makes sense.
Yeah. So that's kind of cool.
Just the fact that the article was written and that you had somebody who was able to quantify how, for example, iron is such a weak color chromophore compared to vanadium and chromium, and to see that the difference between vanadium and chromium is basically vanadium is 4 times weaker than chromium. And basically 100 times weaker than iron titanium. When you are looking at a stone and thinking about heat treatment, what can you do with heat treatment, what can you don't do. Basically, you can cut iron titanium, you can play with the trap holes. Then there are many things that you understand much better when you look at chemistry of a stone. Can something happen here? Oh yeah, that's a strong color agent. Or no, there is just 100 ppma of iron. So basically, you cannot expect to have something bright yellow. Before that, before this article, you just had speculation about, oh, this is a strong color agent or this is not a strong color agent. There was not much data. So just to have already all this work done, you have a range of things that, okay, that's possible, that's unlikely, and things like that. So I think every gemologist can benefit about, having a better understanding about this, and also about a much better understanding about chemistry of color and about spectroscopy.
For sure.
Yeah. Mm-hmm. And so, okay, coming from my background, which is the gem cutter world, and for us as cutters, it's so important for us to understand color, and especially where color is in the stone. What do you think? Is there any information in the article that a cutter can use in their actual day-to-day practice?
Absolutely. So I'm sure you're well familiar with the fact in anisotropic gems, right, that the color, perceived face-up color, is really dependent on the crystallographic orientation of the stone when you cut it. So you can actually use the data because you have the ordinary and extraordinary ray spectra. So the 2 different directions, the different colors that are produced. What you can do is basically model different proportions of the 2 orientations and see what color would be produced. Like, for example, when you look at chromium, the extraordinary ray is the orangey red. And so if you wanted to understand, if you were looking at something that wasn't purely down the optic axis, which is where you'd see just the ordinary ray, what color would be produced if you had some component of extraordinary ray. And chromium is not the best example because it's more similar in the two directions. Like vanadium would be a good example, right, of how different it is. And blue also, right, like iron titanium pairs, very blue when you're looking on the optic axis and very greenish when you're looking perpendicular to it and seeing extraordinary ray. So that would be really helpful.
Yeah, that's kind of an interesting plot.
Master cutters are just doing that without, well, they don't have this circle, but they know that, if you orientate the stone in that direction, you will get, for example, in a ruby, a purplish red. And then if you orientate the table in that direction, you will get more orangey red. If you want to optimize the red color, they make their own calculation based on experience about what should be the best angle in order to put the table. With this type of thing, you can start to model that, and get something out with corundum, and also somewhere with other stone. With every stone that is dichroic, there is an interest to know exactly about this kind of thing. Of course, if the stone is supposed to be, if you take the stone as a homogeneous one, most of the stone are not. So that's another difficulty.
Yeah, you're really gonna have to map it out just by looking at it and then understand. I think it's so cool though, because in my work as a cutting historian, so many things have been said about how much like the science of gemology in the 1900s has really affected gem cutting, especially like in Europe where they're close to gemology educational centers. But most of that knowledge is like from the early generation of gemology, like in the early 1900s when the schools were just starting. So it's kind of exciting to think about, how can in 2020, how can a 21st century gem cutter use really scientific advanced ideas and calculations, not in replacement of what Vincent was just saying, the eye of the master cutter, but in addition to, or to help you become the master cutter, using some really advanced science. So I think it's really cool. I got to think about how could I put that into practice. So maybe I'll have to call you about that another time and think about it, but it's really a cool idea.
Yeah, absolutely. Talk about it offline.
Yeah. So
I think, cutters traditionally will take, if you have let's say 5 ruby crystal homogeneous exactly the same colors, they will cut one down the z-axis, one they will tilt a bit, and then they will see the result regarding the color, and then they will, by experience, they will know that, okay, if I want to get that color, I have to find a piece of rough where I can put the table 30 degrees to the z-axis. That will optimize the kind of problem with that and that. So basically, you model the thing based on experience, but with something like that, you can make some calculation. So people who enjoy, doing a computer program and things like that, you can do it for diamond. Many people are doing that for diamond, but you can also doing that for color stone and putting inside, the different thing associated with the color. Yeah. That will be complicated to do when you have many chromophores. But maybe, in the next 5, 10 years or 20 years, you will have some cutters who will first, for valuable stones, they will make a model and they will benefit because they will maybe don't want to take the risk, to cut the stone in the wrong direction.
Yeah.
Because they want to optimize the color as much as they can.
And I know master cutters now that I talk to, they really do think about it in that way. I mean, I've heard many people say specifically, you're going to angle it this many degrees off the C-axis to make that color, like very specific. It's not even just a guess. It's like mathematically known to them. So
I think I'm nearly, no doubt about it.
Yeah.
Where this really makes my brain hurt though, is when I start entertaining the idea of biaxial crystals. So like trichroic stones, like two different colors is enough. Yeah.
Have you ever tried to model any of these, or you basically just have to measure in 3 different directions, right? Or
gotta collect the 3 different orientations. So it would be very challenging to make up a sample where you can make sure that it was crystallographically oriented absolutely precisely. Yeah. So I would rather work on something isotropic next. Yeah. Like maybe a nice
go for spinel.
Spinel. I think it was like spinel, good target, garnet.
Yeah, one of the guests had suggested earlier garnets. So maybe you know, there's a lot of garnet colors. So
The difficulty will be to have synthetic ones.
yeah, yeah.
Good luck. Oh my god.
So going all
Yeah,
the way back to the
Corundum is okay, but with
Yeah.
garnet on spinel, kind of.
spinel, you can get a range of synthetic spinels, but yeah, garnet not so easy.
Yeah, but you know, some synthetic spinels, like the flame fusion, they are not really synthetic spinels.
Mm.
The crystal structure is a little bit different. That's why you have many difference. It's a little bit like a kind of melted stuff. You know, it's not really crystallized the same way as a natural one.
Okay, okay, I did not know that. So going back to the beginning when you were telling us your whole journey, and you were saying, you know, after a few years of, you know, Bangkok and going back to New York, you left GIA, you started this jewelry brand. So what are you doing now? You know, are you still doing some research, or is your research days over? What's the current life like?
I'm on currently still working some on research on Corundum in collaboration with John, and kind of figuring out, you know, we really need to write up the mixtures of chromophores paper, look at trapped hole and ruby, some of those things that are on our to-do list. And that's where my mind is with it right now. And then otherwise, the past year has been building my own company, like I said, and just joining onto this new startup where we're going to launch in a couple of weeks. So I'm sort of, you know, it's a very exciting lifestyle because I feel like I'm involved in, you know, all sides that I've now had exposure to, which is really exciting. Is kind of where I am with it. And
cool.
47th Street, the Diamond District.
You're still working on that.
Quite a place.
That's a good thing to hear. That you are still here, that you are still working on this thing, and then you know, things are going on, and I will be very happy to see another article in one of these, you know, maybe next year.
Yeah, keep working.
Yeah. So for anybody who hasn't seen it, I'm just going to pop the article back up because it just came out. It's in the new Gems and Gemology. You can download it for free. This is what it looks like. You can get the PDF or you can just read it online. All the data is there, the photos, everything. So definitely check it out. You know, kind of the whole idea with the getting the backstory of the paper was to get excited to go and read the paper. So now everyone who's here with us should, if you haven't already, go check it out. You know, if you've got your copy of Ruby and Sapphire, now I'm going to have to go back. I want to go back and read the chapter because I don't think I ever read that chapter. I just read the ones that I wanted to read for, you know, whatever reason I was working on.
Can you put a quiz and find out how many people, you know, in the people who are the guests of this have read the article? Actually, I'm wondering about that.
We'll have to do that for next time because the quiz, I have to make them in advance. But yeah, this is for next time. There's going to be a quiz. So anyone who's here,
I'm wondering.
Yeah, we're gonna find out next time. But this time you're off the hook. So
okay. So I hope that if there are people who didn't read the article before, you know, the talk, I hope that they will be motivated to read it after the talk. You know.
Okay. So yeah, there's definitely people in the chat that have read it. So. Okay.
Okay.
Good. Okay. One more question just popped up, and then I think we've said everything that we meant to say. Okay. So this one's anonymous. How can opaque corundum be studied using scientific instruments for cause of color? Can the treatments help them become translucent or transparent to study them?
Depends on the opaque.
Say what, Vincent?
I say depends for reason.
Well, certainly.
Oh, I think we lost.
If they're opaque, you're probably not going to be able to treat them enough. Shoot. Can you hear me?
Yeah, you're there.
Am I back?
Yeah.
Okay. Yeah, with translucent to opaque stones, you're probably not going to be able to treat them and get them to be internally clean enough to do spectroscopy. So you would probably be limited to, if you wanted to understand the chemistry, doing things like labs will do EDXRF spectroscopy, which is semi-quantitative at best, or doing things like LAICPMS or SIMS, and that'll give you some insight, but you're just, looking at the surface of a small portion of the stone. So yeah, translucents to opaques are much more challenging to study in terms of color. And you also don't know how much the inclusions are contributing to color. Like there are, scatter off of particles, like in cashmere sapphires, probably makes them look more blue. And how do you really address that? That's something that's not well known.
Yeah, so far, from what I've seen with sapphires that are too dark, with chromium, you cannot do anything. If there is too much chromium, you cannot do anything. So it will be to remain that. Some very dark blue, it was a challenge that many Australian miners were dealing with for many years to try to, when a stone is too dark blue after heat treatment or something like that, how to, bring the stone to a medium blue. They were kind of able to do that with barium, but actually they don't really turn medium blue, they turn greenish or bright yellow. So you can lower a bit the darkness, but turning something from opaque because it's too dark into something that is medium color, I think is very challenging.
This is what everyone wants to do. That's the magic secret that everyone wants to find out.
Well,
if only we all knew, we would all be millionaires.
It's more easy to add color, like develop some color, like with you send something on a trap holes, or you develop a blue with iron titanium, than when you put it inside to remove it. That's more a challenge. Yeah.
Okay, another question just popped in from Suta Singh Barung. Is there any way to measure, I don't know how you say this out loud, iron 2+ in the corundum structure? Is there any way to measure?
So iron 2+, like proportion of iron 2+ to iron 3+, is that the question?
I guess so.
Yep, maybe. Let's assume.
That potentially is the question. I think the answer there is likely no. There's not a technique that I'm familiar with that can be used on gemstones, but the only thing I can think of is Mossbauer spectroscopy, I believe, will give you the valence state of iron, but I'm not sure that you can use that technique on gemstones. And the reason for that might be that it's destructive, or it has to do with the actual analytical method, how the sample is in the spectrometer. But I'd have to dig a little bit deeper into that to see if there is a technique that exists. I'm not familiar with gemologists using a technique, so there's not one that's well known that's applied to gemstones.
I think the ratio between iron 2, iron 3+ is quantitatively, I don't know any method on it's still a big mystery. When you look at a stone, okay, there is iron, but is it iron 2+, iron 3+? You see the iron 3+ absorption, but to get something quantitative that is meaningful, it's
well, yeah, and iron is going to want to be, because it's replacing aluminum, which is a 3+ iron in the 3+ ion in the lattice. So iron's going to want to be trivalent. 3+. It's only going to be 2+. It can only be that way if there's something there like titanium 4+ to cancel it out, so that it's the crystal is electrostatically neutral.
Okay.
Yeah.
Okay. Well, if people want to find you, whether for your jewelry or your research, I've got our closing screen. So if people want to find Emily, she's got Instagram, she's got Facebook. Her jewelry brand has a website. And if we watch these social media platforms in a couple of weeks, we're going to find out the new project, right?
More about the new project. And I should also add, I'm also available because I've had a very winding career trajectory, and I've been fortunate to have people like John and Ken along the way who've been very helpful. If anybody has career questions about any sort of avenue in the gem and jewelry industry, I've been exposed to a lot, and I'm also happy anybody who wants to reach out with questions about that, please feel free
Cool.
to look me up.
Okay. And so, yeah, of course, if you're not following Vincent, if you're not following me, then you can. I've made a shortened link from all of the past webinars that we've done for the last couple of, well, almost 6 months now, I guess. So if you want to see any of the past webinars, there's a little link there. You can type that in. It's a YouTube playlist. And, you know, as we said, the new series is going to be every month. So we won't be coming back next week. We'll be back next month with a new guest. And I just want to say thanks so much to Emily for giving us the story and giving us your time and just, you know, sharing a little bit behind the scenes of what it was like to create an article of, you know, of such magnitude.
Yeah, well, thank you for the opportunity to share, and thank you to the audience for listening. This has been a passion project and, you know, a big part of my life for a long time, and it's been very exciting to share it with you all.
Yeah. Now I realize I'm going to have to really upgrade my understanding of chemistry to be able to ask the right questions for these webinars. So we're all
well, at least you know, you are speaking with a better English pronunciation than me, so you know. No, you're doing great. I really like to work with you on that, and even if you are not a hardcore scientist, yeah, you will see soon some good reason to dig a bit more for knowledge, and you are very good for that. So
yeah.
okay.
So yeah, maybe by the end of whenever the end of this webinar series is 2 years down the road, I will become a hardcore scientist from all of the people that we're gonna speak to. So this is
Science, gemology, it's about, I think after 40 years doing gemology, I will be still learning things. So you have to be, you have to get curious, and you have to get ready to keep learning. That's, I think, the key thing. If you want to do a career in gemology, keep curious, keep reading, and keep learning. Because if you decide to stop learning, then you're going down.
Yeah, and I think
and you have to be okay with knowing when to say I don't know, and it's okay to say I don't know all the time, and you know that's not a roadblock. That's just, you know, a minor hurdle, and you keep searching for answers. But it's okay. There are plenty of things I don't know, and I try and find the answers, and it's a continual learning process.
Yeah, and I think
I love the I don't know. It means that there is an opportunity here to dig a little bit more. And when you stand on this in front of this cliff of the unknown, it's a kind of, oh, I don't know. Okay, maybe there is something to dig.
Yeah, definitely. Okay, well, thank you, Emily, and thank you, Vincent. We'll see you, Vincent. We'll see you next month. Emily, we'll see you around sooner or later, somewhere in the world. So
yeah,
okay.
Absolutely.
Well, I will.
See you. Have a nice.
I'll let you guys go, and
have a good evening, guys.
You too. Talk to you later.